Okay, so global data center capacity set to increase significantly over the next few years. I mean, I guess in general terms, the digital world just demands more data center capacity, and then suddenly the sort of AI explosion has added significantly to that. I mean, the estimates I'm seeing, I was looking yesterday, anything from 130%, and I can't remember who, but some reports six-fold increases in power, which sounds crazy. But just your thoughts as to how, significant is this power increase over the next few years, thanks to data center demand?
Yeah, thanks, Philip. And yeah, I've also read through a number of these projections, and yeah, you're absolutely right. The ones that I found most useful actually cite a range, right? So, for example, McKinsey projects that by 2030 we'll see anywhere from a 3x increase in global data center power demands on the low end, up to a 5x increase on the high end. So either way, it's a significant increase. And the recent purchase of the 3 Mile Island nuclear power plant by Microsoft should be a signal, I think, to all of us that these projections are probably not inflated and that they should be taken pretty seriously. But ultimately, it's not just about scaling, but scaling sustainably and using the technologies available to allow you to do so.
Yeah, and I mean, in terms of I suppose the major focus alongside, they're aware of this power increase. I mean, the data center industry for a long while has been focused on energy efficiency. It's got its PUE metric, etc. But I guess with this high performance compute resource, there's even more sort of pressure to look at energy efficiency. I suppose that in simple terms, to either do more with less power in an ideal world, or at least at the very worst case scenario, do more with the same amount of power. I mean, are those sort of reasonable objectives, shall we say?
Yeah, yeah, exactly. Efficiency has become an important performance benchmark. As photonics technologies are adopted deeper into the data center, I'm starting to see some performance thresholds on the order of picojoule per bit. And this becomes an important consideration when deciding which architectures, which components are the most energy efficient, while allowing your compute resources to scale. At VPIphotonics, we have a unique glimpse into this. We provide simulation software, and our users are the ones who are exploring those different architectures and technology trade-offs. So we don't always know the details of what they're doing, but we are routinely adding new examples into the software as templates as a starting point, just to do that exact type of work.
Yeah, and as I understand it, one of the major challenges is that at high bit rates, the reach of the electrical interconnects decreases, so more power is needed to overcome that. Is that, I mean, is that the major challenge, or is that just one of a number of challenges, if you like?
Yeah, yeah. Yeah, look, copper's great, but it's scalable. It's a cheap option. We should use it as long as we can. But yeah, exactly as you mentioned, as the bit rate increases, the reach of those electrical interconnects roll off, right? It especially starts to roll off once you get into that 50 to 100 gigabit per second range. And so replacing those electrical links with optical interconnects is the natural step. We've already seen this. It's already happened at different stages in the evolution of data centers already.
Yeah, so I'm going to say, obviously, optical interconnects are of particular interest. You said they're already used in data centers to a certain extent, but I think the suggestion is we're at something of a sort of crossover point where they're going to come, if you like, to shorter and shorter distances, for the links connections. Is that what you're seeing? Again, as you say, you're perhaps one step removed but I'm sure your customers are letting you know some of what's going on. Is this where we're headed, I suppose?
Yeah, exactly. Maybe just for a little history. So, yeah, optical interconnects, they're already used in data center networks, right? They have long reach properties because they're using these low loss optical fibers. So they're used for the long haul connections. So, connecting regional data centers together. So that's spanning hundreds, maybe thousands of kilometers. One of the unique things about optical interconnects is that they can be highly parallelized. So either spatially, just by using multiple fibers, or through wavelength division multiplexing, so sending different wavelengths of light along a single fiber, And they can also use more complex modulation formats, so sending multiple bits of information in each symbol. So for those longer reach connections, higher cost per bit solutions are acceptable because there's far fewer of those links. But as we move towards the data center, into data center interconnect, so connecting buildings together now on a single campus, let's say the reach of those is on the order of 1 to 10 kilometers or so. More simpler solutions are needed. So they're using intensity modulated direct detect solutions. So in this case, we just modulate the intensity of light, so not the phase. This is a cheaper option. It doesn't require as much costly DSP or digital signal processing. And then we're also already using optical interconnects inside of the data center. So links that are on the order of, let's say, hundreds of meters. They're using, more inexpensive technologies like multimode fibers and VCSELs. So yeah, now we're at the next inflection point. So yeah, exactly. Reaching data rates where electrical interconnects for connections on that order of, let's say, meters. Yeah, we're reaching the limitations there. And so it's a natural progression to move to, optical interconnects like we've done at other stages in the data center.
And if I understand correctly, this latest sort of development means that photonic integrated circuits, or PICs, are becoming of particular interest for what, I don't know, we call them these new optical interconnects, or the next phase, if you like. Um, and what are the benefits? Why is it that PICs are becoming so attractive for this next sort of step in the optical interconnect journey, shall we say?
Yeah, yeah. Yeah, so, historically, optical interconnects have used discrete components like lasers, modulators, photodiodes, all packaged into a pluggable transceiver. But yeah, more recently, photonic integrated circuits have been used to increase the functionalities, but also to reduce size and cost. For those who are not familiar with PICs, they're photonic integrated circuits. It's basically a chip similar to an electrical IC. So it's combining multiple photonic functions on a single chip. So enabling some new functionalities, as well as some cost, power, and size efficiencies. A common term you'll hear thrown around is silicon photonics, which refers to the material used in the PIC. And this means that those chips are produced on a very scalable silicon platform. But in reality, a number of different materials are typically integrated together on this platform. So it's not just silicon, but also indium phosphide and others. So these designs can actually get quite complicated pretty quickly. Which is one of the challenges in implementing PICs with your optical interconnects. And this is really where like design automation tools come in. They can save a lot of time and headaches.
Again, I've also heard talk of co-packaged optics, at least for the near future, which, I mean, the word hybrid is attached to almost everything to do with IT, whether it's hybrid cloud, hybrid cooling in the data, etc. But am I right in thinking these are hybrid interconnects, so they're combining a bit of copper, a bit of optics, giving you the most cost-effective solution depending on what you want to connect? Is that where we're moving to for the time being, at least?
Yeah, so pluggable transceivers, they've been widely used, and really the main benefit of those is that they're very flexible. They can be swapped out and upgraded easily. But what we've learned, right, is if you package the optics closer to the board and closer to the electronics, that's when you can start to save power and improve signal integrity, and also provide a higher bandwidth density. So to do this, PICs are required for these co-packaged optic solutions. There's a number of companies already doing this. NVIDIA just announced their co-packaged optics based networking switch at their latest GTC. They're working with a number of different suppliers in this space. But you also have companies like Broadcom, Intel, Lightmatter, who've been sharing their latest co-packaged optics solutions as well. So it's here.
Yeah, and I mean, you mentioned NVIDIA there, so clearly the compute companies, they're pretty much committed to this sort of optical computing future. Is there a way in which data centers can prepare for this, whether it's adapt? I don't know how easy it is to adapt legacy facilities because there's clearly a lot of existing real estate there. And then I guess in the perfect world, you've got a nice greenfield site so you can build, for optimum AI focused conditions. But just your thoughts, I suppose, as to what data center owner operators need to be aware of, how they can
Mhm.
prepare for this.
Yeah, so yeah, optical interconnects, they're already being used connecting the data centers and buildings together. But for these AI machine learning tasks, you also want to be able to configure and select as many GPUs or XPUs as needed to train your model. So now these PIC-based optical interconnects, they're replacing copper and they're being used to scale out the network. So what does that mean? So scaling out, typically referring to connecting all the racks together, so that you can actually link as many of those GPUs together to do one of your tasks. So this is what this NVIDIA, networking switch provides. And next on the horizon is for optical interconnects to replace copper for data center scale up, which is, addressing that AI compute fabric. So connecting processing units within the rack together. And you are already seeing, you have a number of well-funded startup companies like I mentioned Light Matter before, but also Air Labs and Celestial AI, all working on solutions in this space. And when implementing such technologies, something just to keep in mind is that PIC technologies have matured over the years, but not to the level of electrical ICs. And we're still far away from standardization. Another challenge is that these co-packaged optic solutions, they're not as flexible as pluggable transceivers. So you should be prepared when failures occur or when upgrades are needed.
Okay, and I guess before we finish, I can ask you, and I don't want to sort of depress people because they're maybe already sort of you know trying to get their heads around what we've been talking about to a certain extent, depending on how well they were. But there is some suggestion that sort of AI focused high performance compute, the sort of GPUs, NPUs, etc. They at some stage are going to give way to quantum computing. I mean, I'm sure everyone has heard the phrase, but maybe doesn't understand. And there was reversible computing, which was a new one on me. But just, I suppose, do you have any idea of where, how and when those might appear, as serious solutions? And also, to our conversation, where do PICs fit within the quantum world, if you like?
Yeah, so the answer is I don't know, but I have some opinions on it. I'm seeing things happen. Will PICs be used in quantum computing? I think so, most likely. If we truly want to scale quantum computers, then they'll be used in the compute engine. And there's some companies working towards this. But I'll also ask the question, what is quantum computing most useful for? Um, as far as I understand, breaking classical encryption is one of the major use cases. And maybe there's a few other tasks it can be used for. Um, so if you ask me if those applications will widely be adopted by everybody, probably not. I I don't think so. So I think yes, governments will be investing in this area. But in my personal opinion, I think we're going to end up with a handful of quantum computers that will need to be networked together. So do I see PICs being required within the quantum computers and for networking them? Yeah, most likely. Quantum computing, it's one of those things where it's always 5 or 10 years out, right? But if you don't have one foot on the boat when it takes off, right, then you're already too late.
Yeah, I get, and again, this is possibly not that easy to answer, but in terms of what we've talked about, is there any particular advice you can give to the data center community in terms of how to prepare for what sounds like an exciting but somewhat uncertain future? I guess flexibility, agility, but what do they need to consider when they're looking at this developing landscape?
Yeah. Good question. I'd suggest about thinking how to scale sustainably, right? think about the technologies that are available and how to optimize them. We talked about for every link length, there's a different flavor of like an optical interconnect solution. And as we move deeper into the data center, there are more and more different solutions emerging, and standards have yet to be fully developed. So, for example, the co-packaged optic solution, it offers the performance optimization needed, but pluggable transceivers offer the flexibility. And each of these solutions will have a time and a place. But companies are putting their own spin on co-packaged optic solutions, so many unique solutions are still becoming available. So it'll be important to weigh, the pros and cons of each solution together. And I really think testing and simulation will really help people make informed decisions about those technology choices.
Okay, well, it's been great to chat, Chris, and some fascinating insights into an area that we don't always explore as much as we should, perhaps when it comes to DCS. We're more interested in the power and the power and the cooling is what folks really get excited. No, but this is a great insight into a rapidly developing space. So really appreciate your time, Chris. Thanks very much. Thank you.
Yeah, thanks, Phil. Thanks for the time.